All right, I think we can start now, Dr. Charlton. Is it okay? All right, so good afternoon, everyone. Um, all right, so first of all, I'm Catherine. I will be assisting all the Philippines account in terms of sales matter, marketing, and any support needed. All right, so I have here with me Mr. Hari Hara. Hari Hara Sudan is currently an application engineer for CAD IT consultant and then part of the technical team that support customer in various discipline domains. All right. So he completed his Master of Science in Mechanical Engineering at National University of Singapore with his course work focus on design and manufacturing. He is specialized in FEA simulations such as linear and nonlinear dynamic heat transfer and advanced coupled field simulation like vibroacoustic, piezoelectric, etc. He is experienced in explicit dynamics analysis for solving highly nonlinear dynamic problems. Okay, such as drop test, crash, hypervelocity, impact, blast structure interaction. He is also providing engineering simulation consulting service and post-sale technical support for ANSYS Mechanical Aqua, Autodyne, and then Granta products. All right, so I think, Hardy, you can show your screen if you have your presentation, sorry.
Hi, Catherine. Thanks for the introduction.
Thank you.
Hi, guys. Thanks for joining this session. So, I think in this session, I'm going to go through ANSYS Mechanical. So, let me share my screen first. I hope you all can see my screen.
Yes, Harry, I can see your screen.
Okay, sure. Now you can see, right? So, yeah. So I believe you all can see my presentation. So, in this session, I'm going to go through ANSYS Mechanical. It's like an overview presentation of ANSYS Mechanical capabilities. So, ANSYS Mechanical is the FEA solver under ANSYS solutions. Okay, so this presentation covers the full capabilities of ANSYS Mechanical, so which includes normal basic static type of analysis, and also dynamic analysis, which includes various types of vibration analysis capabilities. And other than this, we also have some specialized simulations for some specific applications. So I will give an overview of all these different types of applications that can be solved using ANSYS Mechanical. So first, why do we need to simulate? Okay, so I believe you all are familiar with the product design process, right? So we engineers will design the product, and then they have to make sure the product works fine for a specific period of time. Okay, so simulation helps us to design products and to check whether the product can meet the design standards or the product expected standards. Okay, and also it helps to meet the product code regulations. So this is also kind of standards. Then improve product design. So let's say we already have a product, and then we would like to improve its performance or reliability. I will say there's a warranty issue or something. Okay, so then we need to improve the design. Right? So again, simulation helps us to improve the performance of the product. Then root cause failure analysis. So let's say there is an existing product that fails during the operation. So it can be due to many different reasons. So simulation tools can help to find out if there is any structural or some physics related issue with the design itself. So if you are using simulation, you can find out the root cause the design problem, and then you can also rectify the problem. And finally, reduce time and cost of product development. So without simulation, in order for companies to design a product and then bring it into market, it takes a lot of time, because they have to do a preliminary design, then they have to do a prototype, and then they have to check the design, like by applying the loads. So the prototype must undergo some testing process. So all these are time consuming and costly. Okay? But simulation will reduce this whole process. So using computers, we can quickly run the simulation and check whether the design is able to meet the specific standard or not. And also it helps us to reduce the number of prototypes. So instead of doing maybe 10 or 15 prototypes, with simulation, we can just do 1 or 2 prototype, and then we can go with the product launching or something. So this will shorten the product design cycle. And other than the advantages I've discussed before, with simulation, you can also innovate. So simulation, you can try a lot of new ideas, because all these are not cost effective. That doesn't incur any cost. So you can quickly run your multiple designs using simulation. So that helps in driving innovation in the product design, and then manage complexity. So sometimes we might be dealing with some complex parts. So understanding the physics, or maybe checking its performance without a prototype can be difficult. Whereas with simulation, you can even manage complex physics and reduce cost, lower cycle time. So all this we discussed earlier. And why ANSYS? Okay, so ANSYS, most of you have come across ANSYS before. So ANSYS is the world-leading simulation software. So ANSYS provides multi-physics simulation solutions. So ANSYS is not concentrating only on mechanical type of simulation. So ANSYS provides multi-physics simulation platform. Okay. So with ANSYS, you can understand the performance in terms of structural physics, or in terms of fluids or electronics. So you can look at multiple or various different factors and aspects as well. Then we have a best-in-class solver, which is robust, and then we have a reliable workflow, seamless data connectivity, like you can connect and share information from multiple systems, and then simulation. So as mentioned, we have the best solvers. With this, you can scale up your simulation. You can increase your model size. At the same time, you can also reduce your solving time. Okay. So these are the 5 priorities of ANSYS customers, and ANSYS is trying to ANSYS has developed tools to match their customers' requirements, like accuracy, multi-physics, recently electrification. Okay. So these are some of the world-class companies using ANSYS. So almost all the big companies in the manufacturing or product development design sector will be using ANSYS, like US Army, ABB, NVIDIA in electronics. In automotive, we have BMW, Daimler. And then energy sector, we have Petronas, Petrobras, Petronas, Vestas. In consumer goods, we have Nestle, P&G. In medical, we have Pfizer, Philips. So almost in all industries, we have customers who are using ANSYS to improve their product performance. So mechanical product family. So under mechanical, we have a different range of products. Okay. And as I mentioned earlier, ANSYS is providing multi-physics simulation solutions. So ANSYS is not only structural simulation, which is mechanical. We also have fluid dynamic simulations, electromagnetic simulations, semiconductor, okay, embedded software, optical, so and also materials information. So we have like multi-physics solutions. Okay. So now in this presentation, we are going to concentrate on the structural portion. So these are the different tools under or different products under ANSYS mechanical family. First is ANSYS Mechanical. So ANSYS Mechanical is mainly used for stress analysis or strength analysis. So today we are going to go through the mechanical ANSYS Mechanical in detail. Okay. Then we have ANSYS LS Dyna, which is also a structural analysis tool, but for some specialized applications like drop test, crash test, impact test. Okay. Then Autodyne is also another structural analysis tool, but Autodyne is mainly used for blast simulation and blast structure interaction. Okay. So blast and blast structure interaction. Then we have additive solutions. So ANSYS additive solutions are mainly used to simulate 3D printing process. Okay. So later in the coming presentation, I will quickly show a slide on this additive solutions. Then we have some add-on tools like ENCODE. ENCODE is an add-on tool for fatigue calculations, and ANSYS Motion is an add-on tool for multi-body dynamic analysis. Then Sherlock is a tool for PCB reliability study. So today we are going to concentrate mainly on mechanical, and also we'll touch all these tools. So ANSYS Mechanical, this is the GUI of ANSYS Mechanical. So the main advantage of using ANSYS is that ANSYS provides the most user-friendly interface with a lot of automations. Okay. So as you can see, this is the GUI of ANSYS Mechanical. So this is a more user-friendly GUI. So we have like integrated platforms. So multiple components are already integrated. So we have a seamless data transfer. It's easy to use on multi-purpose tools we have here. So before we go into mechanical, first let me explain to you about ANSYS Workbench. Okay. So ANSYS Workbench is a platform. So ANSYS Workbench is a simulation platform of ANSYS that allows you to access all the different solvers within ANSYS. Okay. So as mentioned before, we have multi-physics simulation solutions, right? So this Workbench platform will allow you to access the different physics solutions like structural analysis. So structural analysis is under static structural. Then if you like to do fluid flow analysis, we have Fluent system. So we have a lot of workflows, predefined workflows for different types of analysis in the Workbench platform. So Workbench is not a software by itself, but it is a platform that allows you to access the various different solutions that we have. Okay. So the Workbench platform also allows you to do multi-physics simulation or coupled physics simulation. For example, if you want to do a fluid coupled analysis with structural, then we can do it easily in the Workbench platform. So Workbench platform allows you to connect multiple systems, multiple physics together. Okay. So you can transfer the load from one physics to another physics. So just give an example. So using with the Workbench platform, you can do a fluid structure interaction, just also called FSI analysis, fluid structure interaction. So using this FSI study, you can solve the flow analysis, fluid flow analysis using Fluent or CFX. And after solving the flow analysis, you can transfer the fluid pressure as a load to mechanical. Okay, so this pressure will be applied in mechanical as a load, and then when you solve mechanical, you will be able to get the stresses. Okay, so this is an example of a fluid structure interaction study. Okay, so with the Workbench platform, you can easily do multi-way, like one-way or two-way connections, couplings. Okay. So ANSYS Mechanical. So ANSYS Mechanical is the flagship FEA tool for structural, thermal, acoustics, and various other multi-physics simulations. So the FEA tool of ANSYS is called ANSYS Mechanical, which is the flagship product. So it is mainly used for strength analysis, like if you would like to estimate the stresses generated in the body, or the strains or the deformation due to a particular type of loading. It can be vibration loading, or it can be a static loading. So we can take all these types of loadings into the simulation, and you can apply these loadings and you can check what is the deformation or the stresses developed. Okay. So you'll be able to look at all the different aspects in terms of structural mechanics. Okay. So applications from linear statics to complex transient simulations involving nonlinear materials. So with ANSYS Mechanical, you can do a very basic linear static analysis to highly advanced transient dynamic analysis. Okay. So we have the best-in-class GUI. So as I mentioned before, we have the most user-friendly GUI, and we have a lot of built-in tools within ANSYS Mechanical, like topology optimization, connections, two-way couplings. Okay, so later we'll discuss all these additional tools. So we have the logical analysis routine. So if you take any type of analysis, for example, let's say today you want to do a static analysis, or maybe if you want to do, let's say, a modal analysis to find out the natural frequency modes. So we have a predefined workflow. So you just have to follow the workflow. The workflow is also automatic. Like, I mean, the transfer of data from one component to the another component will be all automatic. You don't have to do any manual. There is no need for any manual intervention. Everything is almost automatic. Okay. So here, as I mentioned, we have a logical workflow starting with, for example, this example is for static structural analysis. So if you want to do a static structural analysis, first, you have to define the material properties. So to define the material properties, you need to go to the engineering data. Then geometry. So you have to have a CAD model, right? So the CAD model is under geometry. Then model. So model is basically meshing. So to do any finite element analysis, you have to mesh the model, right? So the meshing is under model. Then so simulation setup is under setup. So setting up means you have to define the loads and the supports. Then solution is basically solving the analysis, and results is basically post-processing, like checking the results. Like you can plot the contour of stress or strain or deformation. So this is the simulation workflow. Finally, parameters. So parameters helps you to run design iterations. For example, let's say you want to run 10 design iterations by changing the load, for example. So using the parameters option here, you'll be able to run multiple design scenarios or loading scenarios. So we have a logical workflow starting from material property definition up to post-processing and parameterization. So we also have an automatic report generation tool inside. So this is the GUI. So as I mentioned earlier, we have the most user-friendly GUI here. So we have a workflow here as well, like logical workflow, like top-down approach, starting from the geometry, material property, mesh, then analysis settings, then boundary conditions where you can define your loads and supports, then solving, then post-processing, like looking at the results. So all these are integrated within the same platform. So it will be easy for the users to change the design, or like to look at all the different aspects within the single environment itself. Geometry preparation. So apart from simulation, we also have CAD modelers. So the most commonly used ANSYS CAD modeler is called SpaceClaim or Discovery SpaceClaim. So this Discovery SpaceClaim is a more user-friendly CAD modeler. With this SpaceClaim, you can quickly create CAD models. Okay. So this the SpaceClaim is based on direct modeling technique. So which means there won't be any history saved. So with the direct modeling technique, you can easily edit the models, CAD models, or you can easily create the CAD models from scratch. Okay. SpaceClaim is basically a CAD modeler, And using this, you can quickly create CAD models or edit CAD models. So let's say you already have a CAD model and there are some issues with the CAD model. So with SpaceClaim, you can also fix the geometry-based issues. Then meshing. So FEA requires meshing, right? So as I mentioned before, without meshing, we cannot solve the FEA model. So you need to have a proper mesh. So in Workbench, there are two ways to get mesh. One is automatic meshing. So you can let the program decide the optimum element size for your case. So the program will automatically determine the optimum element size when you import the geometry into this GUI. So it is almost automatic. So without any input from the user, the program is able to automatically generate a mesh. Okay. So the meshing is almost automatic. But if you want to take control, like let's say you want to change the size or change the type of elements, or let's say you want to refine one particular surface based on your area of interest. So all this can be also done. So you can take full control of the mesh, or you can also let it be automatic. So we have a lot of options to change the element size, shape, the orientation, alignment. So we have a lot of options for that. So strength analysis. So strength analysis basically is used to understand how the structure behaves under different loading conditions, and also you will be interested in checking the stresses and the deformations. Okay, so this is the main purpose of a strength analysis, to check the strength aspects of the design. Okay. So with this information, if you want to improve the performance, you can improve it. Okay. Or if you want to optimize the model, you can optimize it. So there are multiple options after you are done with the FEA analysis or FEA. Okay. So the strength analysis in ANSYS supports all types of analysis, starting from static linear to advanced nonlinear. Okay. So in nonlinear, we have different types of nonlinearities, like material nonlinearity, geometric nonlinearity, and contact nonlinearity. So we support all types of nonlinearities. And also when it comes to material models here, so we support all types of material models. Like for example, if you are working with metals, then we have a lot of material models that helps you to define the behavior of the metal. Or let's say you're working with rubber kind of materials. So basically they are called hyperelastic materials. So you can also define hyperelastic materials. Okay. So that the material in simulation will behave like a rubber model. Then we have creep. So creep model is mainly used for time and temperature dependent defects. In stability. So in some cases, we may also need to check the stability of the structure. So stability involves checking whether the structure may undergo any buckling type of loading. Okay. So buckling is a common phenomenon in structures, okay, especially slender bodies. Right? So using the buckling analysis, similar procedure in ANSYS, you'll be able to check what is the buckling safety factor in your model. Okay. Durability, and also in many cases, when you design the product, you will also need to look at the reliability aspect. So it is not that the component will undergo loading only once, but it will undergo cyclic loading, like multiple times. Okay, it can be few thousand times, or it can be few million times, depending upon what product you are designing. Okay, so you want to also you will need to also estimate the life of the product. Okay? So using the fatigue tools that we have, you'll be able to estimate the number of cycles of loading the component can take before it fails. So failing here can be crack initiation. It depends on what you define as failure. So with the fatigue module, you can calculate what is the life cycle of the component. So we support all types of fatigue calculations, starting from the high cycle fatigue, which is the SN curve based method, and then we have low cycle fatigue, which can be calculated using strain life method. Okay. ANSYS ENCODE. So ANSYS ENCODE is a special type of fatigue analysis tool. Okay. So it is used for advanced fatigue calculations. Like for example, if you have multi-axial loading conditions, or let's say you are dealing with vibration fatigue analysis, or let's say you are dealing with thermomechanical fatigue. Okay. So or maybe a weld fatigue. Let's say you have a welding in your analysis structure, and then you want to see how long does the weld joint can withstand. Okay. So all these types of special fatigue cases can be solved using ANSYS ENCODE. Fracture mechanics and crack growth. So fracture mechanics is also another advanced topic that ANSYS Mechanical can simulate. Like let's say you have a crack, and let's say you want to simulate the material or the design with a crack. So with the simulation, you can check. You'll be able to check whether the crack will propagate or whether the crack will not propagate. So these kind of different aspects can be studied using fracture mechanics. So this is also part of our FEA analysis. And this is a kind of advanced analysis technique where you can define different types of cracks and see whether the crack will propagate or not. Thermal analysis. So with mechanical, we can also do thermal analysis. Okay. So thermal analysis is basically a heat transfer study where you can apply thermal loads. So instead of structural loads like force, pressure, in a thermal analysis, you'll be able to apply thermal loads. The thermal loads can be energy. For example, let's say you have, maybe let's take this example, PCB. So the chip will generate heat, right? So this heat, so the heat energy will be in terms of watt, maybe 0.05 watt, something, right? So with this watt, you'll be able to find out what is the temperature rise in the PCB. Okay. So this is thermal analysis. So you can apply different thermal conditions, temperature conditions, or energy input conditions like heat flow. Heat flow is basically in terms of what? Heat flow or heat flux, which is watt per meter square, or heat generation from a volume. So all these different types of heat inputs can be defined in the analysis. And with the help of heat input, the program will be able to simulate what is the amount of, what is the temperature distribution on the assembly. Okay. So the thermal analysis can be also steady state and transient. Okay. So steady state is basically static analysis, like constant loading. Transient meaning time dependent loading. So next we have the vibration analysis capabilities. So ANSYS is also able to carry out all types of vibration or dynamic analysis. Okay. And we also have implicit and explicit dynamic analysis capabilities. So first we will go through the implicit dynamic analysis capabilities or vibration analysis capabilities, and followed by this we will also see explicit dynamics. So the very basic vibration analysis is modal analysis. So for modal analysis, we have a separate modal analysis system. So using the modal analysis system or modal analysis, you will be able to find out the natural frequency of the structure. Okay. So this is the output in a modal analysis. So the natural frequencies or the fundamental frequencies of the system or the structure. Okay. So this is the most basic dynamic analysis. Okay. So we have this modal analysis system which helps you to do a modal analysis, and you'll be able to find out the natural frequency modes of the structure that you are dealing with. Okay. And in addition to the natural frequency, you'll also see you'll be also able to get the mode shifts, the participation factors, and all. Okay. So So this is one of the modes of vibration. So after modal analysis, we have harmonic analysis. Okay. So in harmonic analysis, we will be able to apply any sinusoidal type of loading. Okay, sinusoidal loads in the form of sine curve. Okay, so for example, let's say there is a motor operating on a structure, and if there is any eccentricity in the shaft, it may exert a kind of sinusoidal force. Okay, so this kind of sinusoidal loads can be applied on the structure using a harmonic analysis. The harmonic analysis is in frequency domain, so we'll apply the load in terms of frequency. Let's say 10 newtons, for example. So that this 10 newtons will be applied over a range of frequency. So there is a need to define the interaction between the bodies. Okay? Contacts is one of the ways to define the interaction between the bodies in the simulation. Okay, so one of the advantages here is in ANSYS we have an automatic method to detect the contact regions. So when you import the CAD model into ANSYS, the program will automatically detect all the contact interfaces and it will create a contact region. So in addition to contacts, we have bolt connections, like if you're dealing with bolts, so you don't even have to model the bolt threads. So we can handle it using the options in our solver itself. So with ANSYS, you can handle a small component to a very large assembly kind of model. Nonlinear adaptivity. So nonlinear adaptivity is again one of the advanced simulation techniques that allows automatic mesh refinement. So what happens is if you're dealing with highly nonlinear material behavior, then using the nonlinear adaptivity, the program will automatically refine the mesh during the simulation. So you don't have to stop the analysis and restart it, but the program will do it automatically. So it will automatically identify the regions where the meshes are highly distorted, and then it will automatically refine the mesh and continue with the simulation. Then composites. Composites is another area which also is important for structural engineers. Right? So with ANSYS, we have a dedicated tool called ANSYS Composite Prepost. So this Composite Prepost is an advanced and dedicated tool for composite layup modeling and failure analysis. Okay. So normally when you look at laminated composites, so there'll be a lot of layups. So inside the layups, if you have different fibers, matrix, and different orientations of the fiber. So using the ANSYS Composite Prepost tool, you can define all these layers. So you can define the layer thickness, you can define the fiber orientation, you can define the property of the fiber and the matrix separately. So basically, this ACP will allow you to define the micro level details of the composite laminate, and you can simulate the composites. So you can check what happens to the stresses when you use a composite material instead of a traditional material. And then in addition to the pre-processing, we also have different post-processing techniques. So using the post-processing techniques, you can look at the composite specific failures like buckling of the composites or wrinkling or delamination of the laminates. So all these can be also verified, which are very specific to composites, can be also verified using the composite pre-post. So this tool is also part of ANSYS Mechanical. Then we have another tool called ACCS, ANSYS Composite Cure Simulation, which simulates the manufacturing process, curing manufacturing process of the composite. Material data. First is ANSYS Granta. Sometimes if you are working on simulations, you may find it difficult to get the material properties. So in ANSYS, we have a material database called Granta. Okay, so basically I'll go to the next slide first. So it's called, the material database is called Granta Selector. So it is like a huge repository of materials where material properties So you using this Granta selector tool, you can find out the mechanical not only the mechanical properties, all the properties like thermal properties, electrical properties, optical properties, the price of the material, availability of the material, some supplier information. So the complete details of the materials can be found in Granta selector. So it is an add-on tool, but this is mainly used for material selection. Okay. And then we have another small tool called materials data, Granta materials data for simulation. So this is a set of material property that are available for simulation. Okay. So this is basically a material library, add-on material library. If you want to extend the material properties available in the default ANSYS library for simulation. But this Granta selector is not for simulation. It is mainly for material selection. Next is optimization. So we have built-in tools within ANSYS Workbench platform for optimization. So basically we can do two types of optimization. One is parameter-based optimization and the other one is topology optimization. So for the parameter-based optimization, we have a tool called ANSYS Design Explorer. So using the Design Explorer, you can set various parameters in your model setup. Like you can set the thickness of a body as a parameter, or the load that you're applying can be set as a parameter. So you can set various parameters, and then the program within the for all these parameters, you can define a range of value. Maybe you can tell the program that you want to vary the thickness from 8 to 10 mm. So you define a range. Similarly, you can say you want to change the force from 100 newtons to 150 newtons. So you can define a range of values for all the different parameters that you set. Okay. Then based on the parameters range, the program will do some internal calculations, or we call it as design of experiments. So it will solve for a few design points, and then it will create a mathematical function called response surface. Then with this response surface, you can explore your design space. Like you can change the input parameter using a simple slider, and you can check what is the output. Okay? So for example, let's say you want to find out the value of stress and the thickness is 8.8 mm. So you don't have to run a simulation, but using the mathematical function, you can set the thickness as 8.8, and the program will immediately tell you the stress for 8.8 thickness will be maybe 230 megapascal, for example. So without doing the simulation, you can find out the values of the outputs like stresses, deformation. Okay. Similarly, you can also do optimization. Like so this is basically a goal-driven optimization where you can set certain goals. So you can say, I want the stress to be below 200 megapascal. Then based on this, so you can set goals. So based on your criteria, the program will recommend the values. For example, for the same scenario, let's say you set the maximum allowable stress value is 200. So based on this, the program will tell you in order to have the stress of 200, the thickness must be 4.4 mm, for example. So this will be the recommendation from the program. So this is called optimization. So the program, you can see here, the program is running for various iterations for the number of the rifts. Okay. So it is increasing the rifts, and then based on this, you can select which design is suitable for you. Then topology optimization. So topology optimization is basically optimizing the shape of your product. So here we don't set any parameters, but we optimize the shape. So what we can do here is, you can let's say you're designing a component. So you can come out with some rough design for your component. Okay. Then with this rough design, you can do the analysis, the stress analysis. Like you can set up your boundary conditions like supports, and then you can apply the loads. Then you can check the stresses. So after applying the stresses, you can do a topology optimization. So what it will do is the topology optimization solver will recommend you with different types of shapes. So you can see here. So this is the recommended shape. So within the optimization system, you can also set goals. Like you say you want to reduce the mass by maybe 50% or 20%. So you can set your expect the objective. Then at the same time, you can also add constraints. Okay, let's say you in this design, you don't want to modify a certain feature. Maybe one particular portion you don't want to modify. You want to maintain the shape. So you can also add exclusions. Okay? So when you exclude a region, then the program will not touch the region during the design iteration. Okay? So it will retain the excluded region. So it will try to optimize the remaining region. So it is very straightforward. After doing the static analysis, you just go and go to the topology optimization where you set up your constraints. I mean your objective, like want to reduce the mass or maintain the stiffness. So these are the basic constraints, and then you can also add any exclusion regions that you want to exclude from the optimization. So after defining all this, the program will run. I mean, it will solve, and it will come out with a shape. So you can see here, this is the recommended shape. So in this recommended shape, you would have reduced the mass. So reducing the mass means you are reducing the cost of the component. So this is basically called topology optimization. Okay. So it doesn't stop here. Okay. So after you get this shape, you have to convert it into a CAD model, right? So in ANSYS, we have an automatic workflow where you can connect the topology optimization result with the new static structural geometry. So what this will do is the optimized shape from here, which is, for example, this shape here, will be automatically transferred to a new static analysis. And on the new design, you can apply the loads and you can apply the supports, and you can check whether the model is able to take the loads or not. Okay. So this is how you can verify the structure after optimizing it. So the workflow is like this. So we start with a rough design of the component, then we will do a static structural analysis on the rough design, and then we get the stresses, and based on the static analysis results, we will do optimization. So after running the optimization, we will get the shape, new shape. So this new shape needs to be verified, right? So you have to take this new shape to another static structural analysis, then apply the constraints, and then apply the loadings, and then check whether the new design is able to perform as per the requirement and the safety considerations. So this is the workflow for topology optimization, and this whole process is seamless and automatic. So you can see all these are just connecting the systems. Okay? By just connecting, you can transfer the data or the CAD model from one system to another system. Okay, so there's no manual intervention in it. Everything is automatic. Okay. So additive manufacturing. So additive manufacturing is also an important area now where many companies are looking into additive manufacturing for manufacturing the components, especially complicated shapes, or where you want to reduce the number of parts in the assembly or customization. So all these needs additive manufacturing. Okay. So there are also some risks and limitations with additive manufacturing. So one of the issues that's common in additive manufacturing is the build failure. So build failure meaning when you print the part, especially metal, after printing, you may see some crack formation or deformation of the shape, deformation of the part. So instead of your required design, you will get a slightly deformed part after printing. Okay, so these are the common issues that people face during additive manufacturing. Okay. So in ANSYS, we have a simulation-based solution. So this simulation-based solution allows you to check whether the particular part that you have can be printed or not. And it will also tell you what will be the deformations if you print this particular shape, or what will be the distortions or warpage when you print a particular shape. Okay, so this is the purpose of additive manufacturing simulation solution. Okay, so this solution that we have is mainly focusing on metal-based printing. So it is not for plastic printing, because in plastic printing, the cost of failure is not that high. Whereas when you look at metal printing, the cost of failure is very high. So this simulation solution is mainly focusing on additive printing based on metals, mainly powder bed fusion technology printing and DED technology, direct energy deposition technology. So using this, if you are printing any metal parts using these two technologies, you can use ANSYS simulation to check whether the part that you have can be printed without any build issues. Okay, so this is the important aspect. So we have a lot of pre-processing tools for additive print, because in additive printing or additive manufacturing, support generation is also one of the important tasks. Right? So we have an additive prep module which helps you to prepare your model for printing. Like you can convert to STL and fix issues with your STL models, prepare the support, part nesting, and set the right orientations. So all this can be done using additive prep. And we have print simulations. So using the print simulation software solution, you can take the part, you can define the printing parameters. So the machine parameters, basically, like you can set what is the laser speed, and then what is the layer thickness, hatch spacing. So all the real-time printing parameters or the machine parameters can be set in the simulation, and you can run the simulation and you can check what will be the stresses during printing or after print, not during printing, after printing. So what will be the distortions, or whether the support will fail or not. So all these different aspects can be simulated. Then we have a tool called ANSYS Discovery. So this tool is mainly used for designers who don't do any detailed design, but those who want to do some quick simulation. So ANSYS Discovery, also called Discovery Live, is an easy, fast, and powerful simulation for designers. So this is a real-time simulation, which is embedded in our CAD tool. So using the real-time simulation, you can see what happens to the results, like the stresses, deformation, when you modify the part. So it is a instantaneous simulation. Okay. So this discovery simulation is available for basic structural analysis, basic fluid flow analysis, and thermal analysis. Okay. So this is totally different from our flagship solvers. Discovery is mainly for those who want to run multiple design iterations within a short period of time, because this is an instantaneous simulation. So you can see in the video here. So for the fluid flow, they are changing the diameter of the pipe, and immediately the results are changing. Okay. So this is how fast the Discovery Live is. Okay. So just by modifying the geometry, you can check how the simulation results will change. Okay. It's a live simulation. It's a real-time simulation. So this is mainly used for some preliminary studies. It's not for a very detailed product design and simulation, but it's mainly used at the beginning stage. Okay. When you have hundreds of design ideas in mind, then you can use Discovery to narrow down the ideas, okay, or streamline it. So it is an interactive GUI where you can directly change the geometry and you can get the results. Same for structural analysis as well. You can change the increase. For example, you can increase the thickness and you can see what happens to the stress when you increase the thickness immediately. Everything is instantaneous. within few seconds, you will be able to get the results. Okay. So I think this should be all about Access Mechanical. Okay. So if you guys have any questions, you can type in the chat. I will be able to answer it.
Do you have any question? Dr. Charlton, do you have any question for Harry?
Yeah.
Yes.
No, I will do a demo so they can understand. Oh, okay. Okay. No, no problem. No problem. Okay. Let me do a demo so that you can visually see what happens, what is FEA and what kind of results you can get. Okay. No problem. Yeah. So yeah. So this is the, I believe you can see my screen. Catherine, you can see my screen, right?
Yes, Harry, I can see your screen.
Okay, so yeah, so this is the Workbench platform that I was mentioning before. So Workbench is the simulation platform of ANSYS. So in the Workbench platform, on the left-hand side, we have a lot of analysis systems. So these analysis systems are designed for a particular type of analysis. First, for example, let's say we want to do an FEA, strength analysis. And then for the strength analysis, we have static structural. So you can click, drag, and drop it over here. So this static structural will come out with the full template of the full template that you will need to follow. Okay. So first step here is the engineering data. So engineering data is the place where we define the material properties. So since you all are mechanical engineers, so you know the mechanical properties, right? So basically to define the strength of the material, we need few parameters. So the most important parameter here is Young's modulus. So when you go into the engineering data, so you can create your own materials. Okay. So we also have a set of library where you can directly use it. For example, so we have structural steel. So for the structural steel, we already have the material properties defined. Young's modulus is 2E11 Pascal. Poisson's ratio is 0.3. So we need these two properties to identify the stresses generated in the material. So these two are the most basic properties that are needed to get the stresses. Okay. So you can also create your own material. Okay. And you have to define using the isotopic elasticity on the left hand side. Just click, drag, and drop it over here. Then you can define the properties. Okay. 1.6 11, for example. And you have to define the Poisson's ratio. Okay. You have to define the Young's modulus and the Poisson's ratio. Okay. So these two are the basic properties needed to run the stress analysis. So without Young's modulus, we cannot calculate stresses. So we have to define Young's modulus and Poisson's ratio. So these are the material properties, which are basically user input. So after the engineering data, we have to have a CAD model. Okay. So if you already have a CAD model, which you have created in other CAD tools, you can just right click and import the CAD models. If not, you can also create CAD models from scratch. Okay. So I'm using ANSYS SpaceClaim, which is ANSYS' own CAD tool to prepare a CAD model. Just wait for a minute for SpaceClaim to load. So this is the Space Claim platform. I'm going to create a simple CAD model here, just a block. So Spacecam is a very user-friendly tool, so you can easily, edit models. So let's say you want to increase the length, you can just click and drag. It's very simple. So very simple to edit models. So let's say you want to create a hole here. It's also very simple. So you can easily create a hole like this. Okay. So using Spaceclaim is very user-friendly to build models. So now I have a 3D CAD model. This is a CAD model. I believe you all know CAD model, right? 3D CAD. Next, I'm going to the simulation. Okay, so this is the ANSYS mechanical UI. So this is very user friendly and interactive. So you can zoom in, you can rotate the model, you can select the different entities. Okay. So here on the left hand side we have the project outline. So where when you expand the geometry, you can see the bodies that are created in the CAD. So in this model, I have only one body, so you have only one. So if there are multiple bodies, everything will be listed under the geometry. Okay, and you can see the material. So the material that is assigned by default is structural steel, but if you want to assign then maybe the newly created material which is test, then just click on test. So the material will be applied. Okay, then meshing. So meshing, as I mentioned before, it's automatic. It's almost automatic. So you can just right click on the mesh and choose generate mesh. The program will automatically create a mesh. So you can see here, the mesh has been created automatically. I did not do any setting. Okay. But if you want to, let's say, refine the mesh, or if you want to define your own element size, then you can also define it over here. Okay. So as I say, I changed the units time. I put 2 mm element size. Then right click, generate mesh. Then you'll get a defined mesh. So you can see this is 2 mm element size. So this is how the program will, you can control the mesh. So you can let the program decide the shape, the size, or you can change it. After you generate the mesh, you can see a tick mark. Okay. Now, under the static structural, we have to define the loads. We have to define the boundary conditions. So boundary conditions includes loads and supports. So when you right click on the static structural, insert, you can see a lot of loads and supports. So first I'll define a sub, which is a fixed support. So when you define the fixed support, yep. Yep. Okay. Okay, the nodes will be generated during meshing. So, okay, let me highlight the nodes. Okay. Correct. Oh, okay. So in ANSYS, in the new versions of ANSYS, the program is automatically selecting the material, the element type. Okay, but if you like to do it manually, you can. So you just have to type the element number using the command, and then the program will automatically use the material, the element type that you specify. Okay? If not, the program based on your analysis type, loading type, the program will automatically select. So it is intelligent enough to automatically select the element type in the new. Yes, yes, no, rubber. So because rubber is hyperelastic, so that it will automatically change the type of element. Yeah, yeah. So it's more user now. Okay, yeah. No problem. Yeah. Okay. So now we are applying a support. So first, you have to specify the location where you want to apply the support. So I'm choosing this surface. Okay. So I'm applying the fixed support on this surface. Now I have a support, and I also need to apply a load, because without load there won't be any deformation or stresses, right? So I have to apply a load. So I click on the static structural, insert, force. So I'm applying force load. Force. I'm applying the force on this surface. Then I have to define the magnitude of the force and the direction of the force. Okay. So because force is a vector quantity, so you have to define the magnitude and also the direction. So instead of defining using the magnitude and direction, I'm choosing something called components. So when you change to components, it will be very straightforward. You can define the x component of the force, y component of the force, and z component of the force. So say I want to apply a vertical load in vertical downwards, maybe. So I put minus 100. So you can see an arrow mark here acting downwards, and the magnitude is minus 100 newtons. So this is the force of minus 100 newtons acting downwards. Okay. So we have applied a support and we have a force. Okay, then we have a mesh. So without a mesh, we cannot solve FEA. Mesh is important. Now, we can solve the analysis. Before solving, let me also request for some results. So I'm going to insert maybe deformation. So I want to see what is the total deflection of the material. Now I can solve the analysis. So right click on the solution, solve. Okay, so the solution has been solved, and you can see the deflection. Deflection is 0.06 mm. So this is the deflection. Now, let's say you also want to see the stresses. Okay? So you can insert one more result, solution, insert. So you can see here we have a lot of results: deformation, strain, stress, contact results, reaction force. Okay? So let me insert stress. So if you go into stress, we have a lot of different stresses: von Mises stress, principal stresses, normal stresses, shear stresses. Okay. So let's insert von Mises stress. Okay. So the stress generated on this component is 42.3 megapascal. Okay. So this is how you can run a FEA to check the strength aspects. So the stress generated is 42. So based on the stress, and let's say you know the yield strength of the material, then you can calculate the safety factor. Okay. So then you can verify whether the safety factor is enough or not. If it is not within your required safety range, then you need to modify the design, something like that. So this is how you can use ANSYS FEA in your product design to check the strength aspects, basically stresses and deformations. You can see the yeah. Force. Yeah. Oh, this is typically downwards, the bending load. Yep. Oh, okay. So okay. No problem. So when you run FEA, so you will not get a single result. Normally, when you do calculations, you'll get only one number as a result. But in reality, the the stress will not be constant throughout the model. So it will be a changing stress. So that is the advantage of using numerical methods. Okay. So for the results, we have something called probe. Okay. So I'll just use this probe to explain this. So the result. Okay, so when you click on this element, this portion, the stress is 28 megapascal, whereas this portion, it is 26. And here it is 19. And near the hole, it's it's quite high, 24. I believe you all know stress concentration effects, right? Stress intensity factors. Then when you go down here, the stress is very low, 1 megapascal. So this color is a contour plot because the stress is not a constant value, it is a distributed value. Okay? So the maximum is 42 and the minimum is 0.46 in the entire model. So whenever you we design, we will use the maximum value because maximum value is the point where the stress is very high, and which is probably, if the part fails, probably it will fail at the maximum stress location. Right. So this is usually we will be checking at the maximum stress region. Okay. Red basically is low on certain points. Yellow is nearer. Clear the blue. Yes. Correct. Yeah. So I believe this is similar. I believe you have studied the cantilever bending. Right? So the lower portion will undergo compression and the top will be under tension. And this is the neutral fiber where the stress is almost zero or neutral fiber. Right? So it's the same example, cantilever. Okay. So similarly for the deformation. So deformation. So you can also think logically here. So when you apply the load and the support is here and the load is applied here. So this portion will undergo large deflection, the maximum deflection, whereas this portion is fixed. So it's zero supported. So that's why the stresses are maximum at the support. The stresses are minimum at the free end because the free end will not have any stress. But it's free to bend. Yeah. So this is the structural mechanics principles. So we can just take the same model here. So I'll just connect. Okay, we have a model analysis system. So in Ansys, you can easily connect the systems. Now let me go to model analysis. So model analysis is basically to check the natural frequencies. So again, the same principle. We have the materials defined under the geometry. In mesh, I click generate mesh. So I create the default mesh. Then in a model analysis, you don't have to apply any loads. You just have to define the supports. Okay. So I'll define the fixed support. Right click, insert, fixed support. So you can see there are no loads, only supports. Okay. Fixed support. I apply the fixed support on the surface. Now you need to also specify how many modes you want to find. So let's say 6 modes, the first 6 modes. Right click. And so it's very simple. Model analysis is very simple. Okay. So here in the table, you can see there are 6 natural frequencies found. So the first frequency is 1827 Hertz, then 2794, then 10,357 and 377. So these are all the different natural frequency modes, the first 6 natural frequency modes. Okay. So if you want to look at the shapes, then you can also get it. Mode shape results. So this is the first natural frequency, which is 1827 Hertz. Then this is the second frequency. Okay. Then this is this is like a twisting mode. Then we have the fourth natural frequency. Then we have the fifth natural frequency, which is this. Then the sixth is a tension mode, the tensile direction. Okay, so we managed to extract up to 6. So if you want 10 modes, then you can just put 10 here and the program will extract the first 10 frequency modes. Okay, so this is the modal analysis. Yeah. Okay. Oh, okay. So, so in mechanical design, in certain applications, we would like to have make use of the natural frequency vibrations, and in most places we try to avoid the natural frequency based vibrations. Okay, for example, say you are dealing with a ship design, not a ship, maybe a bridge design. Okay, so when you are designing a bridge, normally people will look at all the different natural frequency modes to make sure that no wind load will excite any of the natural frequency modes, because when, let's say, there is a wind load at the same frequency range, and it may lead to resonance. So when during resonance, the amplitude of vibrations will be very high and it can fail the structure. Okay. So in some scenarios, we try to avoid the natural frequency. For example, let's say this is a structure. Then let's say you have a motor rotating on this structure at a particular frequency. Okay. And again, assume that the motor is exerting a force. Since the motor is rotating, it will apply an alternative force, right? Like a sinusoidal loading, which has a frequency. So when the frequency of the motor matches with the natural frequency of the structure, then at that particular instant, you may see the amplitude of vibrations to be very high. Okay, so this is an undesirable scenario because the noise will be higher. Okay, so amplitude, yeah, be higher, and the noise will be also higher, right? So people will try to avoid these scenarios. So what they will do is they will try to make sure that the natural frequency is not overlapping with the operating frequency of the machineries. So this will prevent the amplitude of vibrations to be. This will make sure there's no like lot of amplitude, high amplitude vibrations in the system. So this is one scenario. But in some scenarios, like for example, if you are working at ultrasonic transducers, okay, so that people will tend to have more amplitude vibrations because ultrasonic machining is making use of resonance. So especially this kind of tensile mode. Okay, so you can, I just put it like this. So the ultrasonic transducer will be acting in this in the length direction, so it will be moving up and down. So in this scenario, we will like to use, we will apply the loading in this range so that we can excite this particular natural frequency in our design. Okay. So in a transducer kind of scenario, people will try to apply the load in the range, in the last mode range, which is, for example, 19,800. Okay, for this particular material. So when you excite this mode, then it will, since it already has a natural frequency here in this range, you'll get more amplitude vibrations, which is a desirable phenomenon in this particular application. So in certain applications, we will make use of the natural frequency vibration, and in most scenarios, we try to avoid the natural frequency based vibrations. Okay, so depending upon what type of application we are looking at. Okay, so this is so that's why modal analysis is the fundamental, where you can at least understand what are all the different modes, different mode shapes, and the directions and all. Okay. Yes. Ah, yeah. Okay. So for rotating machineries, for example, so, okay, normally this is not a shaft. So this is not a rotating thing, right? So if you have a torque, then again torque also has a torque load also has a magnitude based on the RPM. So we try to avoid if the component is not rotating. Okay, so we try to avoid this. But for rotating machineries like shafts or bearings, so we have a separate set of analysis called rotodynamics. Okay, so the rotodynamics analysis will help you to check whether you might have come across Campbell diagram, the critical speed. Okay, so those kind of aspects can be studied using rotodynamics. That's mainly for rotating machinery, rotating components like shafts and bearings. But for a structural type, yes, again, this is like, especially when you have a torque kind of loading, then we try to avoid this kind of frequency. So to prevent the yeah. For that, you need to avoid. Yeah, correct. So especially for this particular scenario, it's the third mode which we need to avoid. Yeah.
Uh, Hello. Yes, sir. Sorry. All right. Okay. Sure. Sure. Anyone has question now? Hello. Mm-mm, yes. Yes. Correct. Yes, po. Yes. Right. New. Yeah. I understand. It's okay. Yes.
Yes. Yep. Or if nahihiya man, sir, pwede nyo i-chat dito sa chat box. Yeah. Tapos babasahin ko na lang for Harry. And then I drop my email address, my mobile here. If you have any question in future, you can just message me anytime. Yep. Yep. Chat nyo na lang sa chat box. Cut po. Yeah. Yeah. Kung wala kayong WhatsApp, Viber, or Telegram, pwede kayong mag-connect sa akin sa Facebook, and then Messenger para mas madali. Mhm. Yes, yes. Yes po. Email address. Yeah, I have their email address. Maybe I can drop them an email with the link for the feedback. Then after submission of the feedback, you can get the certification. Okay. Apo. Apo. No, he's still here, Dr. Charlton. Yep.
Oh, yeah. So I believe this session has been useful to you all. So normally for this, this FEA can be used even in your final year projects or whatever design study you are undertaking. So whenever you try to design a new component, so it can be based on metals or plastics or any type, you can use simulation to check whether the design is performing as per your expectation. So this tool can be used in your final year projects or in your internships. Wherever you design a component, you can make use of ANSYS simulation tools. Okay? So when you get a chance, you can try the tool, and then if you have any questions, or let's say you want to discuss whether this particular tool can be used in your research or in any areas, you can discuss with us, and I think you can contact Catherine and she will be able to help you with it. Okay.
Yes.
Anyways, thanks for joining, guys. Yeah, thanks, Professor. Yeah.